but I'm not posting the recordings. I need to take some time and post recordings every day. I keep forgetting to do that. Because we have one student whose computer is broken and is trying to get it fixed. So anyway, time to start class. Let's go ahead and get going here. So we are going to be in yeah, well, I can do that right now. The chapter 2 is due when? Tomorrow.
Saturday, I think.
Chapter 3 we need to do like next week. Make it due next Saturday. And did we finish going through all of chapter 2? Chapter 5. And that puts us, chapter 7 would be the 4th. November only has 30 days, right? That's not right. I'm going into November when I should be like. This is exam 1-6, so this should be 10/24, not 11/24, 10/24. And then this one should be 10/31, so that'll be Halloween. Halloween's on a Saturday? And then 9 would be first Saturday in November. Where's chapter 10? There we go. Would be the second Saturday in November, which would be the 14th. Oops. And then let's see. I don't remember if we do another exam after chapter 10. It doesn't look like we do. So then we do chapter 11, which would be 11. Did I already do a 14th, 21st? Chapter 10 would be, chapter 9 is, wait a second, what's going on here? Chapter 8 was 10/31, chapter 9 is 11/7. Chapter 10 then would be the 14th. Chapter 11 would be 21st. Chapter 12 would be the 28th. No, but we have Thanksgiving in there, right? So that would be the first. That would put us at the Thanksgiving is this week here. So we come back from Thanksgiving and we put that one on the 5th. So that's 12/5, chapter 11. Nope. Chapter 12, 12/5. And then chapter 13 should be 12/12/2020. And I think the last day of class is the 17th. So that puts us right on schedule. So that's good. So if we can crank out a chapter a week from here on out, we'll be fine, which I think is doable. It's the first couple of weeks and the first couple of chapters are always a little bit more challenging to get through as we learn some basics and kind of get some fundamental things under our belts. So this is the end of the third week, right? Or is this the end of the second week? September 11th, we started. No, this might be our second. I don't remember. End of the second or third week of class, whatever it is. But anyway, we're in good shape. We can get all this done, I believe, without too much trouble and pain. We're going to go all the way through chapter 6 and then have an exam. And that actually gives us, we actually have kind of a week of leeway right there, another week to get something else done if we need to push these off a little bit. We've got an extra week in there. And then chapter 7 and on takes us to the end of the semester with 1 week per chapter, which I think is reasonable. So,
I have a question. What will the exams kind of look like?
that's a good question. So we have just the one exam right here is kind of a midterm, and then we have the final exam. And I can't remember what let's take a look at what the syllabus said. Oh, here it is, syllabus. Which one is this one? Let's see what it said as far as the amount of weight we give these. So the midterm exam is apparently worth 20%, and it's because there's supposed to be 2 of them. But because there's only 1 of them, we'll actually probably change that to be worth less. It'll probably be worth more like 15%, and then the final would be worth 20% in this case of the course, just because we only have 1 midterm. But anyway, the exams are open book. You may not use your notes, but if you have taken your notes in your book and the test is open book, then you can use your notes. And the reason that I do that is I want to encourage students to get to know what's in the book and get to know how to read physics out of a book. It's important to be able to read technical things out of a book like that. You can print off the book and write the notes in by hand. You can type the notes in using Adobe Acrobat and print them off. You can use the electronic book and have your notes in there because you've signed into OpenStax and you've been highlighting things or whatever and taking notes. You can do it that way. It's up to you. I don't care how you do it. But if you have notes in your book, you can use those notes and you can use the book. But nothing else will be allowed except for blank scratch paper, pencil, calculator, those kinds of things. Don't care what kind of calculator. We do prefer that you don't use a cell phone calculator, just because a cell phone calculator, of course, gives you access to the internet and all that stuff. Yeah, for physics, it doesn't really matter what kind of calculator. You're usually just going to use it to calculate the sign of something or whatever. In physics, you're not really doing anything. I mean, you can have the most fancy calculator in the world, and it really won't make a difference in physics, because the hard part is not usually the math. It's not usually the calculations. It's usually setting up the stupid equations is the hard part in physics. Once you've got that done, you've pretty much finished the problem. So anyway, yeah, those are the kinds of things you'll be allowed in the exam. If you would like, I can provide you with, or you can find your own physics kind of cheat sheet thing. They make them like this, and I've got a few of these left still. You can also, I've got some periodic tables that's, I don't remember if we use them in this class at all. I don't think we do. Next semester we might use them a little bit, but not much. this class doesn't use the periodic table that much. We kind of skip over a lot of those things to make room for all the mechanics we do.
Would the physics cheat sheet kind of just have like the formulas and stuff on it?
Yeah, it just has, it's kind of like a short form um, of the formulas that are available. The problem with these physics cheat sheets is that they're all a little bit different, and some of them are completely designed for use with a particular book, so the notation is a little bit different. If you can figure that out, if it doesn't bother you that the notation's a little bit different for each thing, then you're fine. In this one, I don't see the notation being terribly different. They're using I hat, J hat, K hat for their unit vectors, it looks like. They're using a different notation to denote vectors. Instead of an arrow over the top of the vector, they're using a line under the vector, which is a less common version of that, but it's still used. Everything else looks pretty similar. There's nothing else really weird going on. And then it can be quite useful, and I can send you one if you want, or you can pick these up at a lot of different places online, or whatever. You can even download them and print them. If you want to download one and print one for use in your exam, just please send me that formula sheet in an email, so that I can just look at it and see that it compares to the ones that I give out, so that we're all kind of on the same ground. You want one of these?
Okay, I think I just want one that you probably gave out. So
Okay, I'll send you one.
okay.
And I think I might be out at this point. I have 2 left that I can send to you guys in the cook, and then I'm done. I started with like hundreds of these things. I don't even remember where I got them. I got them for free from somewhere, and I just started giving them out to students over the years, and now I'm finally done with them. So you guys get my last 2, as far as I can tell. Yeah, I'll send those to you today, and you'll be good to go. And they're useful. You'll probably use this for years to come if you're going to be in engineering.
Okay.
These are the kinds of tools. They've made a really good sheet here that is just full of things that are extremely useful. So yeah, that's definitely a good tool, and I'll send that.
And will the questions kind of look like the problems that you give us through WebAssign?
So that's the next thing. They will look very much like that. In fact, I will use the same questions that I gave you in the homework in the exams.
Okay.
The difference will be that the parameters will change because WebAssign randomly assigns parameters to the problem.
Yeah.
Also, a difference will be on the exam is that you will not have any help options available. You will not be able to just click on the book and it will just take you to the book. You'll have to go and find where it is in the book that you need to go. You will also, I don't know that many of these WebAssign problems have given you videos yet. I don't think so, because not many people have linked to these particular problems to videos yet, and I haven't had time to do it myself. I don't even think I can do it myself anymore. I don't think they allow teachers to modify these problems anymore. But anyway, you won't have any like quick resources available to you. Of course, you won't be able to email me from the problem. You also will only have usually 3 attempts on problems. Multiple choice problems, it'll usually be 1 attempt. That kind of thing. So it'll be a little bit different. It'll also be timed. So I'll usually I think I give 2.5 or 3 hours or something for exams. And usually they're about 10-ish problems, maybe a few more, maybe if I don't remember exactly how many. I can actually look that up really quick.
Does it usually take students like the whole time then?
I've had students that have taken up the whole time. That's pretty rare. Usually the average time on these exams is probably about, I would say, a little bit more than half the time that I give. So let's see here, exam. This exam has 11 questions on it. For the average student, takes 138 minutes to do this exam. And I think that I give, I don't remember how many minutes I give. It's got some timing on it somewhere. Here's the timing. Oh, it doesn't. Show me there. The timing is Hold on a second. I have to close this so that you don't see important things on here. Okay. Okay, so on this particular exam, I give 200 minutes. That's actually 3 hours and 20 minutes. That's a lot of time. But I would say that my average student probably spends an hour and a half ish. They're probably about the average time that they say 138 minutes ish. So, no, 138 minutes is over 2 hours. I'd say most of my students spend less than 2 hours, and probably an hour and a half to 2 hours on the exam, is my guess. But I give you all the time. I think that I give you a sufficient time that if you're struggling with something or whatever else, you don't really have to worry too much. I've rarely had somebody really take up all of the time. But you can if you'd like.
Would you like us to turn in our work too? Just so like, let's just say we have a simple problem.
So when you take the exam with a proctor, they will collect your work from you and they will send that to me, I believe, or they'll keep it for me or something like that. So yeah, you'll definitely turn that in with your proctor. All right, so that is the exam, and there are 11 problems on the exam, like I mentioned. The exam, what else can I say? It's due by 5 p.m. So when you make your appointment, make sure that you give yourself all of those 3 hours and 20 minutes in case you do need to use them. So if you're doing it here at the college or whatever, they close, I think 5 p.m. is about when they close every night, or a little bit after that actually. So you definitely want to get in there by 2:30-ish, 1:30-ish to start your exam. Anytime before that. If you're proctoring with somebody not at the college, I keep this thing at 5 p.m. for just to be nice to these proctors so that they're not, proctoring an exam during dinner time or something. So try to keep it at a time that works well for your proctor. Can't think of anything else that needs to talk about. Anybody have any questions? Any other questions about the exam? It's not coming up for a while, but no? Okay. Well, looks like that. So we've got a month and a week before exam one. The first exam comes along, which covers chapters 1 through 6, and then the final exam. So something that is often asked when we get to the final that you should know is that the final exam will be comprehensive. It will cover chapters 7 through 13 in the same way the first exam covered chapters 1 through 6. In other words, questions taken from the homework. Anything that is comprehensive coming from chapters 1 through 6 on the final exam will have been already on exam 1 through 6. So I will only draw from exam 1 through 6 for the final exam when it comes to the exam, and this is actually the final exam, I think, for this class. 2110 final exam, because I created a new exam. And that one looks like it has 16 questions on it. And those come from pretty much all the chapters. So trying to think. I don't think I have anything in here from chapters 1 or really from chapter 2, because chapters 1 and 2 are kind of review and learning vectors. But all that vector stuff that you learn is covered in other chapters in real time in the physics. So you won't have to I don't actually have to draw anything from chapters 1 and 2. So any other questions then for the final or the other one?
Well, I don't think so.
So we've got a pretty good schedule here. We're going to finish up chapter 2 today, and then we'll start chapter 3 Monday. You'll have chapter 2 due tomorrow, I guess. So
We don't
tomorrow.
have very much chapter, but we were like over halfway done.
That's great, because Yeah, the last part of 2.4 was the multiplication of vectors, right? And we'd actually just kind of quickly covered cross product, but we'll go over that and we'll review dot products in more detail. And then we'll do some examples here. What's this 2.4 the last section you said? Okay, good. So yeah, we'll do a little review of these and then talk about cross products in greater detail here real quick. All right, let's unmute the video. There we go. I don't know why they call that video mute. Why don't they call it video blind? I don't know. Anyway. Okay, so just to review, there are two types of vector multiplication. And vector multiplication, of course, is weird because how do you multiply directions together? Vectors have direction. Well, the first type of vector multiplication doesn't multiply directions together. What it does is it tells you how much of one vector is pointing in the direction of the other vector, and then it multiplies those lengths that are pointing in the same direction together. So if we wanted to kind of conceptualize the dot product, are you seeing my screen right now? It doesn't look like you are.
No, I'm not.
Let me see if I can get that back here for us. Gotta remember how to find my screen share. Here we go. Screen share. This one right here. Okay, so here we are. So if you want to visualize this idea of the dot product, you can think of it like this. You have your coordinates, x and y, like this, x and y. And we have two vectors. Let's say that we have a vector. I'm going to start each vector at the x-axis just because it makes our lives a little easier. We have vector 1, v1, and here we have v2, v2. And what the dot product does is it says, okay, these vectors are pointing in different directions. How much of v2 is pointing in the direction that v1 is pointing? And so what it does is it takes it's like it takes a projection. Remember when we talked about projections? It's like you shine a light that is perpendicular to v1 on v2, and v2 casts a shadow on v1 so that you get this portion of v2 that points in the direction of v1. And then you take this length, the part of v2 that points in the direction of v1, multiply it by v1, it's all pointing in that direction, and you get a number. And that's the dot product. It tells you how much of v2 is pointing in the direction of v1, and then it multiplies that by v1, by the length of v1 or whatever. And it works the other way as well, v2 and v1 this way. If you project v1 onto v2, you get the same kind of thing here, except that you get a bigger projection onto v2, and it ends up getting, you know, the projection of v1 onto v2 is actually bigger than v2, but you end up getting the same answer. And so the dot product is actually commutative. You can A dot B is equal to B dot A, in other words. And I think they talked about that here. Let's see here. Oh yeah, right here. A dot B equals B dot A. So it's commutative, which is great because that's kind of like normal, kind of like a normal multiplication idea, right? It's also distributive. So if you have A dot B plus C, you get A dot B plus A dot C, and so on and so forth. And the math of doing this is really quite simple. If you know the angle between the two vectors, you can use this version of the dot product right here, where you just take the magnitude of A times the magnitude of B, or the length of A times the length of B, and multiply by the cosine of the angle between them. And that really is the projection. That's literally how you do a projection. And you can see them doing a projection here. Here's that projection. Here's that projection. Either way it works, right? But the great thing about this form of this is that if you do know the length of A and B, you can actually calculate, and you know the value of the dot product between A and B, then you can actually calculate the angle between the two. Well, then how would you know the actual value of the dot product if you didn't know the angle? Well, there's another formula for this which comes from the vector form, or the component form of the vectors, where you just take the x components and multiply them together, and then the y components and multiply them together, and the z components and multiply, and these are all magnitudes. So the magnitudes multiplied together, and you just get three numbers, and then you add them together. And those numbers can end up negative because the magnitudes can be negative. If the x component of A is pointing in the negative direction, then you have to put a negative on this component here. That has to have a negative on the magnitude of that component. So these things can end up positive or negative, but in the end, you just add them together and you're good. That'll give you the total dot product. So if you do have, if you know what the components are of each vector, or you can calculate it from the angles and magnitudes, then you can calculate the dot product here. Then you can use that value in this formula up here to calculate the angle between the two vectors. And they actually give a formula for that down here, right here. So this is that formula. You do the dot product, you divide by the multiplication of the two magnitudes, and you get that is equal to the cosine of the angle between the vectors. Take the inverse cosine of both sides. And you're good. So in this dog example, we have these three dogs pulling on this stick at different angles, and the forces are given in component form here: force 1, force 2, and force 3. And they want to know the angle between the forces, force 1 and force 2, and you just use this formula to do it. Pretty simple. So they calculate the dot product. Go ahead.
In that formula, I mentioned Z will be working with 3 dimensions in this section.
I probably do give you a problem that's in 3 dimensions in the homework. Yeah, I probably do, just because the math of it is not really any different than, yeah, just gives you a little experience. We will see 3 dimensions in this class from time to time, particularly in the second semester.
Okay. So also on the homework, I know you're gonna cover cross product, but it does like the dot product times the cross product. So how would that look?
So it does like vector 1 dotted with vector 2, kind of like that, and then crossed with vector 3.
Yeah, I think it's just like V1 dot product and then parenthesis V2 and V3. Yeah.
Well, that's better. That's easier to explain. There is a rule for if they don't put the parentheses in, that you must do the cross products first before you do the dot products. And the rule is really easy to explain, I suppose. If it makes sense to you, I suppose it's easy to explain. If you do a dot product between 2 vectors, you get a scalar, and then you can't do the cross product, right? So you have to do cross products first so that you end up with vectors, and then you can do dot products. So all 3 of these being vectors, if we did the dot product with this and this first, then this would become a scalar, and it would be scalar cross vector, which is not allowed. So you always have to do cross products first, and usually they put parentheses around them just to make sure that that is done. So when you do this, you literally just figure out what this answer is. Do the cross product first, and that will give you a vector V4.
Oh, okay.
Do velocity 1.
Okay, I was wrong. So on the homework, it's like A dot product F and then D cross B.
So it's
Just
A
like 2 different ones.
dot product F like this.
Yeah, and then it has parentheses around both of them, and then it's D cross B.
And then D cross B.
Yeah.
Okay. So in this case, it's a little bit different. In this case, you can do either one first, and it doesn't matter. And then you do the results will give you. So this is just going to give you a number. It's just going to give you a scalar number. It's not a vector. And then you'll have a number times this cross product. And this cross product is going to give you some vector that is the result of that. And then it's just a number times a vector.
Okay.
That's,
So like it's going to give you like the j hat and I hat of the cross product, right?
yeah, so this cross product, you'll end up with some vector, and this vector might look like, 3i hat minus pi k hat or something.
Okay, and then you just distribute the dot to the
Yeah, if
vector.
this is like 2 out here, then this becomes 2 times 3 and 2 times pi,
Okay.
and then you get 6i hat minus 2 pi k hat.
Okay.
Yeah, and really it's really more of a comfort thing. You start to realize that these dot products and cross products aren't really all that mysterious. You just have to remember that they do something very different. And then it just becomes really, really easy to deal with because it's just another operator. It's just like a plus sign or a divide sign or whatever. There are rules and there are things that work and things that don't, and you figure them out. And wait till you do linear algebra. When you do linear algebra, you'll be doing stuff like this where you have and you're like, solve that. You're like, what the heck does that even mean? Right? But in fact, this actually is very similar to what we were just doing with cross products and dot products. It's just a completely different way of approaching it. It's different notation, essentially. And because vectors don't necessarily have to be in a component form like we were using them. In linear algebra, you're using mostly matrix form of vectors. So the matrix, so if you have a vector like this, let's say we have a vector 4i hat minus 3j hat plus 12k hat. This can be represented by a vector that is where we use this, we call this bracket notation, in other words, bracket. But they call it bracket because this is called the bra, and the other side is called the ket. And I don't know where the C left. The C is the stuff in the middle, I guess, for the bracket. I don't know. But anyway, they call this bracket notation where the notation goes like this. It's 4, -3, 12. So it's essentially an ordered grouping of numbers. And it's the reason for it is because it's much easier to write. And then all of a sudden, this can be put into mathematics where this right here is actually, let's see, this, I'm trying to remember what this notation does. I think this one is actually 2 cross products. So this cross this, cross this. So, but you can also have these things be represented by a matrix of numbers, which is now your vector. A vector can be a 3x3 matrix, for example, or something like that, which is really useful when you're doing high order mathematics for computer science, for computer programming. There's all kinds of physics that uses this. Einstein is one of the ones that kind of pioneered this so that he could do his theory of general relativity. And all kinds of other physics uses this as well. So there's lots of uses for it. And it's one of those classes that most people take this class after they're finished with calculus. I took it in the middle of calculus, after Calc 2 and before Calc 3. I should have taken Calc 3 first, it would have helped. But anyway, it's there's a lot of Calc 3 stuff that you can do with this notation. And it cuts your paper and writing down to about half or maybe even a third of what you would have to do in normal notation. So, all right, so moving on. Let's see, let's clear all that out. Any other questions before we move on from dot products? Okay, so in this particular case, they're using the dot product to find the angle between vectors. And that is one of the great uses of the dot product. There are other things that you can calculate that require the dot product to calculate, or the dot product makes it easier to calculate. One of them is a type of energy we call work, which we talked about a little bit last time. And work is, when you're talking about work is the amount of energy required to move something from point A to point B. And that work is calculated by figuring out how much force is being used in that direction. Because not all the time, you're not always pushing in the same direction that something's moving. For example, if I push on a lawnmower, I'm actually pushing downward, a little bit because the handle is pointing downward. And then my force goes through that handle. So my force has to be pointing downward a little bit. But the lawnmower only moves forward. It doesn't move down through the grass, right? It gets squished into the grass a little bit, but then it stops. So its movement is almost all horizontal, but the force is both horizontal and down. The downward force doesn't contribute to the energy to move the lawnmower. It just is pushing the lawnmower a little bit, making it a little closer to the earth. The forward movement of the lawnmower is all from that forward part of the force, which is only part of the force. So that part of the force is determined by the cosine of the angle between the force and the movement. And so that's where the dot product is used here, and that's exactly what they do here. They use the work is equal to force times the distance, or force dot distance as vectors go, and they're using the vector component version of the dot product, which is great, works fine. Now onto the cross product, again, the other type of multiplication of vectors. In this one, like I mentioned before, in this one, we're usually creating a vector that represents something that is not necessarily physical. Why? Well, this is often used for rotational things. When we're rotating, the force that keeps something going around and around in a circle is not constant. It is constantly changing. How do we know that? Well, the best example of this is to roll a bowling ball along a nice smooth floor. And I have a nice smooth floor here, and we could do the example, but it'd be difficult to really show it. And my room's a mess right now. We've been doing all kinds of other projects in here. But anyway, as you roll this ball along the floor, you just start it rolling. It's not going to follow a circular path. The floor is nice and flat. It's just going to roll on a straight path. However, if I wanted to roll on a straight path, I'd have to push on it. I'd have to exert a force on it. In what way do I have to exert that force? Imagine that you roll the ball forward and then you're walking along on the right side of the ball as it's moving forward. Which direction would you push the ball if you wanted it to go in a circle, if you're standing on the right side?
You push at an angle to it. So I'm trying to explain it. It's like if you have a spinning disc and you push on it down.
So here's my ball. It's rolling this way right now. I want it to roll in a circle like this. That's the circle that I want it to follow. Okay, now we're going to do a quiz. We're going to make this into a quiz. So get out, open up an email and send me an email with your answer to this quiz, or you can write it on paper if you're right here in class. That's fine too. And we'll have our friend Brandon, we'll have him do this when he watches this video as well. So Brandon, when you watch this video, do the quiz and send me an email. Which direction are you going to push this ball to make it follow this circle? And I'm not talking about one push. I'm talking about a push that you're going to have to continue to do. So I'll give you some different points where you have to tell me which direction that you're pushing it. Here are the different points. Which direction are you going to push it when the ball is right here? And then assuming that you push it in all the right directions to get it to this point, which direction are you pushing the ball when you get here? Which direction are you pushing the ball when you get here? You're going to push the ball the whole time. Which direction are you pushing the ball? And you can draw a picture if you want, or you can explain it. Drawing a picture would be the best. Which direction are you pushing the ball to keep it going in this circle at each of these positions along the circle?
Do you just want like cardinal directions or what?
You can use cardinal directions if you want. We could call this north and this east, or you could call this X and this Y. Or you
Okay.
could just draw this picture and draw an arrow. I'm pushing the ball this direction, for example. Or I'm pushing the
Okay.
ball this direction. Whatever you want. I think that drawing the picture would be the easiest, honestly, easiest for me to understand and for you to do. So why don't we just have you do that, draw a picture and tell me which direction, show me by arrows, whichever direction you point your arrow, which direction you're pushing the ball as it goes around the circle. And now I'm going to go to stop share. No, that's not. Yeah, stop share. And I'm going to go to polling. And I'm going to add a question. Title for this poll: direction. Circle force direction. Direction. Anonymous. Keep it anonymous. Nobody knows. So my question is, which direction do you push the ball? Keep it going in a circle. Now, if you can answer this question at each position with a single sentence that covers all those positions, that'd be great, because that's actually going to be the best way to answer this question. But I will give you, let's see, do we want it to be single choice? So this will be, I'm going to look, this is going to be the bottom left position. I want to know which direction. So bottom left position, is it going to be up, which is the Y direction, positive Y direction, or down, which is negative Y, or is it going to be left, or is it going to be right, and I'll, those positive and negative X. And then you'll be able to choose more than one.
By bottom left, which do you mean?
Oops, dang it. I deleted my question instead of saving it. I'm not going to waste any more time then, since I accidentally erased my question. Oh, well, that was failed. I've only used that once before. Okay, let's see, where were we? That was a big fail. Okay, so just send me your email when you've got your thing done. If you're not sending me an email, that's fine. Tell me what you think. Let's go back to my sharing on my page here. So what do you think? What was the drawing? I don't remember the drawing. Where's my page? There we go. I must have. But my drawing had a circle, and what did it look like? So there's one on the bottom. Oh, the bottom.
That's what I'd like to ask.
Oh,
His top, bottom, left, right.
I think that I did one like this. I think I said that my three positions were going to be here, here, and here, I think. Or maybe over here, but it was somewhere off. So which direction do you have to push this ball if the ball starts off going this way? Which direction do you have to push the ball to get it going in this circle.
At a right angle to the force.
What force?
So if the force is going this way, you have to push at a right angle this way to make it go this way.
What do you mean the force? There's no force
Well,
on this ball.
force, it has a constant velocity.
So the direction of the ball is this way,
Yeah,
and you have to press it perpendicular to that.
yes, towards the direction you want it to
So I want it to go this way. Well, I want it to go in this circle. Which direction at this point do I need to push this ball to make it go in the circle? Left, right, up, or down? To
Left.
the left? Okay, so
Yeah.
that's my force. That's what and you agree with that?
Yeah.
Okay. How about up here? Which way am I pushing here?
South.
Down, right? South, down, negative, right? How about here?
To the right.
To the right?
Yeah.
Like this?
Yeah.
So this one is perpendicular to the velocity. This one has the ball's velocity is this direction, and this one's perpendicular to the velocity. This one, the ball is this direction, and we're not perpendicular to the velocity anymore.
Okay.
So what do you think this one might be?
It's like northeast.
Yeah,
If
like
you-
that.
Yeah.
That creates this pattern all the way around, right? And that is correct. If you actually roll a bowling ball along a floor and you try to keep it going in a circle, you'll find that you will be pushing it towards the center of the circle every time. Always towards the center of the circle. So this is kind of weird movement. It's not very intuitive. Most people actually say, well, you would push it this way. That's not true. And also people say, well, it's like when you're in a car, you turn a corner and you're getting pushed out this way, but that's not actually happening. You're just trying to go straight and the car door tries to push you in. So the car door is pushing you towards the center of the circle or the seat belt or whatever that you feel pushing against you. So yeah, this is called the centripetal force, and it's weird. It has this weird 90-degree thing going on, first of all. Force one way, velocity another way. It's obviously causing movement of the object, but it doesn't actually change. If you do this experiment with zero friction, you will not slow down the ball at all. The speed will stay the same, but the direction that it's going will change constantly. Which is weird, because you'd think that if you were adding a force to the situation, that you would be adding speed to the situation, but you don't. You change its velocity, you change the direction of its velocity, but you actually never change the magnitude of the velocity in this situation if you're only pushing 90 degrees to the velocity. So it's a very weird situation. And rotating things, twisting things, orbiting things, they're all very weird. And so what we have to do is we have to create, since the force is changing constantly, we can't say what is the force that causes this thing to go in a circle. Because there is no what is the force. The force is changing constantly. We can't define that. We can define the magnitude of the force, but we can't define the direction of it. So what we do is we create a new vector that is constant in its direction and constant in its magnitude that can be used to describe this situation that's kind of weird. And the way that we do that is by using the cross product, because the cross product creates a completely new vector that is 90 degrees to the two vectors that you had to start with. The two vectors we had to start with were velocity and force. And when we take, more correctly is actually the displacement and the force, so the direction that it's moving and the force vector are the two vectors. And we do the cross product between them and it creates a vector that's 90 degrees to both of them. So in other words, it's coming, in this particular case, it's coming out of the page, okay? So we have a vector that's coming out of the page which describes this situation. And if we take r cross f, which is the distance that it moves this way, crossed with the force that's being applied to it this way, then we get a vector that comes out of the page, it's coming right out at us, and we call that the torque, technically. And the torque is a combination of the force vector causing the turning and the distance vector that is associated with essentially the movement of the object at that particular point in time. And the torque doesn't change direction as this thing goes around and around. It stays in the same direction with the same length. as it goes around. As long as the velocity stays the same, the force stays the same, it's great. The radius stays the same. Then that torque vector will remain in the same direction with the same length the whole time, which is much nicer to deal with. We don't have to deal with this changing force all the time. But the torque actually doesn't mean anything, technically. Technically, the torque is just a vector we made up to describe this strange situation. And so that's the cross product. In the cross product, you can calculate the magnitude of the cross product, the length of the torque in terms of torque, by using this formula. It looks very much like the magnitude of the dot product or the actual dot product thing, right? But you can only use this if you know the angle between the two vectors. So if you don't know that angle, you have to use actually the component form, which is much more complicated than the dot product component form. So here's the component form of, so this is how they work it out to begin with. And then this is the result of that. This will actually give you the magnitude and the direction. It'll give you the entire vector. It will tell you which direction it's pointing. It will tell you the magnitude of each component. You have to break them, each one of the vectors down in components, multiply them together, do some subtraction, and then multiply by the different components here. And sometimes these things will turn out to be 0, sometimes they won't. It just depends on the two vectors you're taking the cross product of. So they do a magnetic field example because charges in magnetic fields are often moving in circles. So we got that kind of strange thing going on there. You could also do a torque example. But that is the gist of the two types of vector multiplication that we'll do in this class. So enjoy your weekend. If you have any questions on the homework over the weekend, please email me. I'll try to check my email. I'm not very good at checking email on Saturdays, but I try to. If your email doesn't get answered, then I'll just answer it on Monday and we'll extend the homework a little bit so you can just finish that up.
Okay. I have a question about the lab.
Yes. Did you
So
get?
I just got it in the mail today, I think. I haven't opened it, but
Okay, so what I'll do is next week I'll start sending you activities that you will complete and instructions and everything else. So yeah, you're on your way.
okay.
That's it.
This is
Oh,
my
yeah.
quiz, and then I will be in after my next class to do that.
Okay. Stop recording.